Well, good morning. My name is Colin Runciman, and in case of doubt, this is the first lecture session in a first-year computer science module called Mathematical Foundations for Computer Science. So, without embarrassment, if that means you're in the wrong place, now would be a good time to leave. But for everybody else, welcome to this first lecture session. I have with me two of our trusty postgraduate teaching assistants, whom some of you may meet if they happen to be assigned to your problem-solving class. For today, they're reduced to the humble office of being my porters. Thank you, guys. This is Rudy on my left, Michael on my right. They're going to hand out some materials to you now, so receive those from them. Thank you, chaps. Let's do that. So as they do that, let me explain what you're getting. So these are courtesy copies of the digital material I shall use in lectures to save the rather pointless exercise of you busy trying to copy everything down when you can see perfectly well that I've got it on file somewhere, so why can't you have it? Perfectly reasonable question. You will have it, okay? So you will have courtesy copies. Please make use of them, bring them along. You'll hopefully find them something of a handy reference when we do problem-solving activities. I have left a reasonable amount of space around the slide copies. That is deliberate. These are not your notes. They're courtesy copies of my slides. So at various times, you may want to add your notes, and I encourage you to do that as we go along. So that's what you are hopefully now all receiving a copy of, a courtesy of Rudy and Michael. So the other thing to mention, just as we get started, there are just 2 lecture sessions each week, and I try to make every lecture have a purpose, which is clearly indicated. We'll get to that in a moment. So every lecture has a purpose. We don't sort of revise and come round and round again in circles, so be careful of that. A lecture will explain a topic, and then we move on. The next lecture is about something else, the next one about something else again. There are only 12 lectures altogether. Some modules have rather more than that. So I've done my part not to make things too onerous for you. Hopefully, you'll find you get value from every lecture. So do try to make it along to every. Sooner or later, you'll be tempted to miss one. Well, that's your choice, but people do then find they quickly get behind and, oh dear, you know, I don't really understand what's going on now. So I look forward to seeing you, and I'll try to make sure it's worth it. So there are these 2 lecture sessions. They happen on Tuesdays. Beware of a gotcha. It doesn't just sail through with the same pattern right the way through the term. It comes in 2 blocks. So we do for 3 weeks, lecture on Tuesdays, and then a problem-solving class. For that, you're divided into 3 groups. Look carefully at your own personal timetable to see which group you should come along to. If everybody came along at once, the room would be too full. So there are problem-solving classes. There's one on Wednesday morning, there's one on Thursday morning, there's one on Thursday afternoon. You only need to come to one of those. Check your timetable to see which one it is. So that's the pattern for 3 weeks. Lecture, problem-solving class. Lecture, problem-solving class, lecture, problem-solving class, and then we have a little pause for breath. And in week 5, I will not give lectures. There will not be the usual problem-solving classes. However, you should still be at work to catch up, revise, make sure you're on top of everything, because in week 5, there will be what's called a formative test. So generally, when we do problem solving, that's collaborative. I'll encourage you all to work together, do stuff, you know, pretty informally. The test will be a solo effort to check, both for you and for me, how are you all getting on, okay? And then that whole pattern repeats, starting from week 6, another block, lecture, problem class, lecture, problem class, lecture, problem class, another formative test in the following week, leaving time that the last week of undergraduate term, week 10, we have no sessions, which may be good for you because you may be trying to catch up with other things. It also means there is time for you to get feedback from that second and final formative test And if there are things you still don't understand, to find me and ask for any assistance you need, finally to get on top of everything, which you need to do because in January you will take an exam about it all. More of that later. Does everybody now have a copy of these lecture slide materials? If anybody doesn't, please wave an arm, and Rudy or Michael, I'm sure, will get to you in just a moment. Anybody not got a copy of these lecture slide materials, please wave. Your last opportunity. Okay. Thank you, guys. You are released from your labors if you just leave the residue there. That's great. Yeah, take them back, ditch them, whatever. Yeah, that's good. Okay. All right, we're nearly there. These are preliminaries as you gather. We'll get to some maths in a moment. The other question that can crop up from time, I'll ask you in a moment if you've got any questions, but the last thing that is an obvious one, people sometimes ask, are there books? Do I need to buy a book? Is it an e-book or an actual physical book or whatever? So first of all, this is not a module in which there is a book and what's more, we're following it like a sleuth and, you know, it's essential. No, it's not like that, okay? We are not following a book and therefore you don't have to buy a book or obtain one. But if you like the idea of checking out the topics that we're looking at in books, I've made a few suggestions. You'll find those online on the module description and module web pages. So I've recommended several books. Somebody might be out there saying, yeah, several books. That makes it complicated. Please, make my life simple. I've just arrived. If you were going to recommend just one book, fine, okay. If you want that, there's this one. There it is. It's one of the nice things about using this imager thing. I can actually put things on, you can just pop them up like that. So this book, this really is the book. I have it in my hands. You can see it's about that thick, so it's not too intimidating. It's paperback. There may be some second-hand copies around from past year students. I've recommended this book before, so don't rush out and buy a brand new one, even on Amazon. You'll get it much cheaper if you can get a second-hand copy. So if you want a book, you may find don't, but if you want one, there you go. There's a book. You could try that one. This is not a topic where, there's only about 2 books in the whole world that you can get. There's plenty of books about the discrete maths, the foundational maths you need for computer science. There's lots of books. If you find something, for 50p in a second-hand bookshop, you think, well, this is about discrete. It may well be really useful, grab it. So there's plenty of books out there, and there's plenty more in the university library. If you're a very mathsy sort of person, and you're really disappointed that poor old Haggerty's book is actually not that fat, and you would like a fatter and more mathsy book, okay, you might try something like this. You can see it's more serious because it's black. Discrete Mathematics for Computer Science, and yeah, okay, it's fatter, okay? There's more stuff in there. This, in some respects, will go beyond what we need for this module. Not necessarily in everything, but I mean, it's got lots of stuff in there and a bit more besides. So, that's if you're the sort of more mathsy person, give me more in my book, you could try that one. The details of these are online on the module webpage, so I'm just rehearsing. On the other hand, if you're the certain sort of person who tends, if you're honest, occasionally to feel a bit outfaced by too much mathsy stuff, and you wouldn't mind a more sort of gentle, now let's not do too much at once sort of book, but which is also got lots of sort of practice examples, and basically is a bit simpler and doesn't push things quite so hard, well, you might try something like this. There's a series, The Essence of Computing, and they have a volume, The Essence of Discrete Maths. My problem with this is that rather like, vanilla essence, in places you get about 2 drops and you think, is that it? And frankly, no, that is not it. So it really doesn't go, doesn't give you quite enough. But on the other hand, if you just feel like something, just a bit gentler, please, give me the real basics. you could try that to start with. But caution, caution, it really doesn't go far enough in a number of respects. Yes, I've got a question here. This book is written by this chap called Neville Dean. I emphasize again, these are just 4 examples. They're not, if you can't get this book, you're lost. No, no, they're just illustrative. Finally, moving on rapidly, Christmas is a little way off, isn't it? But if you happen to have, a rich auntie out there somewhere who's already saying to you, oh, you've gone to university, what can I buy you for Christmas? Well, you might have other ideas in mind if she happened to ask you that. But if you don't, there are out there encyclopedic hardback books, which are, really just everything in life you could possibly want to know about discrete maths, slickly produced, usually from across the water, from our friends in the USA, who produce these kind of, heavy books, and, sort of 700 pages, copiously illuminated with diagrams, examples, and so on. This one, if you're going to go for something like that, this one I can recommend, Discrete Mathematics and its Applications. It's beyond the 3rd edition now. This just happens to be my copy. It's Ken Rosen. So this is tried and trusted. So do not go into a bookshop and ask how much this is if you value your health, because you will pass out and wake up in A&E and they'll, you say, what happened? And they say, I don't know, they mentioned this huge sum of money and then I collapsed. So, yeah. But if you have the aforementioned rich aunt, she might not pass out. So that could be okay. But treat her gently. Finally, just occasionally people say, hey, sometimes we do proofs. Yeah, that's true, we do proofs. And some people, if they're all honest, they say, just occasionally doing proofs makes me feel a bit nervous. Well, okay, we could talk about that. But another book, if that's you, there are books like this one by Daniel Solo, which is called, nice straightforward title, what it says on the tin, How to Read and Do Proofs. There you go. So this is very much supplementary, extra, if you really want that kind of thing. It's not too thick, and it's just aimed at maths in general, nothing too high-powered. There you go, some book recommendations. If you need more information, you can always ask me. Right, let's now talk about something to get started in our discrete maths. So I said, each lecture will have a topic. Today's topic, here it is. You should have this now in your copies that you've got. Here's lecture 1. We're going to talk about truth values, and we're going to talk about something called logical propositions. So, come on, this is maths. We all know that sooner or later we're going to get into squiggles. We know that. That's the way it goes. When you do maths, you end up with these funny-looking squiggles on the page, and they mean something, and you have to play clever games with the squiggles. That's a kind of rough description of maths. So the question we might ask right early on is, in the end, what do these squiggles mean? And when we start off by looking at logic, the answer is, well, when it comes down to it, what these things mean, I'm going to just zoom in here, is quite simple. And we'll have a rough and ready definition. We'll make it a little more refined in a moment. But a statement, a bunch of squiggles, a math statement on a page, is a collection of symbols. We'll be as vague as that for the moment. And the key point is, it has a value. Don't they always? You're used to that from your school days. You write down some bunch of stuff, and it's arithmetic. So when you work it all out, it's a number. Not here. Here, when we work it all out, it's going to be, for the time being at least, a truth value, either false or true. So there you go. If you thought that everything at university was more complicated than it was at school, you're wrong. At school, you start off with really complicated things like numbers, of which there are loads, and you do stuff with them. Well, now, much simpler. We knew this was coming. We're computer scientists. It's all about on, off. 1, 0. False, true. Okay? Okay, so, for instance, bear with me here, we're going to make things a little more mathsy in a moment. So far as we've said things up to this point, I could write down a bunch of squiggles, and no doubt you can all read it. It appears to say, Paris is in France. And the question is, of course, well, what is the value of that? Now, I'm sure many of you are thinking, well, this is easy, and you've shown us, by the way, that the value is true, and yeah, I absolutely agree that, because every fool knows, surely at least this, that indeed Paris is in France. Well, actually, if you were to talk to some residents of New York, they might not be too happy with that. They might get very argumentative because there is a suburb of New York called Paris. Maybe they even live there. And they're going to say, you're trying to tell me I live in France? No, you're wrong. So the point here is that here are some squiggles that are open to investigation or interpretation. They will be either true or false, but to decide which it is, in some cases, we need to look out at the real world and make some basic observations and say, well, is that true or is it false? Another example, 2 plus 2 equals 6, which in the usual arithmetic world you were taught at school would be false, but who knows, there may be some weird arithmetic out there somewhere in which actually that's true. I don't know one. So those are the basic statements. So far, all we've said is, yes, maths are squiggles. The key point is our squiggles will have a value, and when we finally bring something down to a value, for the time being, it'll be nice and simple. It will either be false, which we shall write capital F, or true, we shall write capital T. And of course, quite soon, we need to start putting things together to make bigger squiggles. We call the symbols we use to do that connectives, and they just make bigger statements out of smaller ones. And we're going to start our explorations by looking at maths operators that correspond to the intuitions of and, or, and not. And for many of you, this will be familiar ground. It won't be the first time you've seen these operators, but if for anybody at all it is, don't worry, I'm about to tell you about them. So these are the symbols I shall use for the operators and, or, and not. You might be used to using other symbols, I understand that. Those are the symbols I shall use, and in particular, in case these symbols for and or are unfamiliar to you, we'll see a good reason for that choice in just a moment. So, what do they mean, though? That's the question. So, the meaning of these squiggles, these operators, can be given by what we call a truth table. When you were at school, in all likelihood, somebody somewhere made a huge fuss, a quite unnecessary fuss, in my opinion, about you learning your tables. And as a child, tables can seem a kind of endless treadmill of misery. And, you know, finally somebody tells you, so you think you've got it cracked. You know, you've learned everything up to your 20 times 20 table, and you're sort of super equipped. Well, what makes you think you've cracked it? Do you not know the numbers go on forever? What is 31 times 37? You mean you don't have that in your table? So you end up feeling a certain sense of dismay and disappointment if you're not careful. Well, the happy news is we need to have no such dismay and disappointment when we make truth tables, because there only are two values, and so the table really, really is all of it. Okay? We just need to ask, well, I'm going to write something of the form P and Q. Well, P and Q must be some kind of squiggles or something, and they have a value, true or false. Well, hey, how many possibilities are there? Each one is either false or true. So here are all the possibilities, each row representing one possibility, and we just say, in each case, what is the output of the AND operator. So AND, as we know every day, you know, this is the case and this is the case. Well, that whole statement is only true if both things are true. That's the bottom row. And in all other cases, if either one thing isn't true, or indeed they're both not true, well then the output is false. So that's logical and then we have a very similar looking table. Squeeze that one in. Yeah, you can just see the top part of that. Yeah, we'll just see that fading away at the top. And we've got a very similar looking table for logical OR. And in this case, if they're both false, well, then the result is false. But if the first thing or the second thing or both are true, then the result is true. Now, from time to time, to give you a little break from me and to help you ask yourself, am I following this, we'll have a little pause with a Q in a box, which, as I'm sure you can guess, stands for question. So there's a little break from me, a little chance for you to think about something, talk about it with your neighbor. So there's the question. I've just said that if both P and Q are true, then the result is true. And that may be, that actually, we could debate that. I mean, in everyday, if I say to you, would you like a cup of tea or coffee? And you say yes, you do not expect me to give you a vile-looking mug that contains both tea and coffee. We're at some really low-grade motorway service station or something if I do that. So, whoa. But I'm very deliberately, I'm saying, no, I'm going to make OR inclusive. Why do you think I'm doing that? Have a little discussion, and then we'll come back in a moment. Go. Natural lull, very good. Okay, so do we have an answer? Any offers? Yes.
It's because it's the OR is to do with a statement of a question. So when asked, do you want tea or coffee? And you say yes, that means that either you want tea or you want coffee. You could want either with tea or coffee. That doesn't necessarily mean that they...
Okay. So this is a sort of philosophical reinterpretation of desire for tea or coffee, which is cool, okay? Thank you. That there is a more mathsy reason, if you like, but I like that as well. Okay, any other offers? Yes?
It's the difference between an XOR gate and an OR gate. So like if
Thank you.
Like we use an XOR gate because it's exclusive. We don't have both. It's one or the other. An OR gate is inclusive because we can have both.
Thank you. Okay, so our colleague here answers, well, we can always have the other one. If we're worried that, we haven't got exclusive OR, well, we can have another operator for that, so we can have our cake and eat it, so let's not fret. Yeah, but okay, given that though, why do I deliberately choose that I say, well, no, I think inclusive OR is a good choice at this point. Yes, let's go over here. Yes. Okay, depending on your electronic substrate, maybe you can make a very fast inclusive OR, but it's harder for exclusive OR. Substrates change all the time. Who knows, maybe that's true, but interesting answer. But again, it's not quite as what I have in mind that I'm aiming for. Yes?
The OR gate was thought of in terms of questioning whether there was a presence in either of the inputs, not in terms of a question in a sense. I think that the TOCOPY question, an OR gate, OR in semantics are different to an OR gate. OR gate is questioning whether there's a presence of either one of the possible inputs.
Okay, so this is similar to our first answer, and it's looking at the kind of philosophical setting almost of what is the purpose of ORness out there, and therefore how could the maths help us? Okay, thank you for all those answers. They've all got some validity to them, but actually the fundamental reason why one would choose to go for the inclusive rather than the exclusive OR is because of this mirror principle. If we look now at the tables for and OR arranged right next to each other, we can imagine having a mirror here. And if in the mirror false reflects as true and true reflects as false, we can see that actually the and the or are just mirror images of each other. And that will make our work a lot easier. Essentially, we have half as much to know, because once we know what's going on one side of the mirror, we immediately know what's going on the other side of the mirror. So that's cool. And it means that the maths works out much more smoothly. We'll see that in a bit more detail in a moment. But that's I say there's validity in all the points that people raised, but this is my particular reason, of course, in the company of many logicians and logic teachers before me, for introducing inclusive OR as the fundamental operator first. Okay, and the only other operator that I want to introduce in this lecture is negation, and the good news here is this really is light relief, very, very simple indeed. So if we've got a statement, we can negate it, which states the opposite. So P is not the case. And we can even draw up a truth table, and the truth table here, because there only is one input, is even tinier. The input is either false, in which case the result is true, or it's true, in which case the result is false. It's as simple as that. That is a negation operator. And we've got a little example, just if you want to track that you're sure that you understand so far what and or and not means. I'll let you track that through for yourself. There's no fresh conceptual material. Okay, so now we can regroup a little. We had our opening statement when I was just talking rather loosely about squiggles. And let's, more specifically, this kind of logic that I'm starting to tell you about is more fully known as propositional logic. And the formulae that we write we refer to as propositions. So a proposition then is a statement in which, and we've already started to do this without making too much song and dance about it, the basic sub-statements, once we get down to, we're not putting things together anymore, we've got down to the things themselves, well, they are just variables. And the point is that these variables, it is understood, could be either true or false. Those are the possible values they take. And that might be determined by observation or by connecting your circuit up to some other box of tricks, which is going to send it the true and false signals, or whatever. So this is rather like the moment where we admit, okay, basic sub-statements like 2 + 2 = 6, we don't always just here and now have a value for that, true or false. It's a variable which is understood that it could be true, it could be false, and we're interested in both cases. So let's just give it a variable name. Perhaps you remember that moment when that happened at school. I can remember it. I thought my arithmetic teacher had taken leave of their senses. You know, I was used to eating up every Monday morning or whatever it was, problems like 31 times 37. And then one day they came in and started writing things like, you know, x plus y. And I'm thinking, that's not a number. X, that's weird, you know, and this is the abomination that is algebra, as some people see it, or, of course, the delight that is algebra, as other people might see it. So we're doing a kind of algebra, and we have variables. Key point to note, however, these variables just have false and true as their possible values. And again, as we've begun to see, if you think about it, a proposition then involving n different variables, each of which could be either true or false. So how many different possible cases are there we need to think about? Well, it's 2 for the first variable, times 2 for the next one, times 2, and so on. And altogether, if we really want to pin down exactly what this proposition means, we'll need a truth table with 2 to the n rows. There are 2 to the n possible combinations of values of those input variables. So previously, we'll come back to logical equivalence in a moment, so not to distract you, I'll just cover that up. So previously, we've looked at the basic truth tables for and or, and not, but it is a simple matter to make up the truth table for any proposition. So here's a simple example. Suppose we've got not P and not Q. Okay, we can build that up. Some teachers and writers choose to look at the values in columns directly beneath the individual symbols. Fine, if you're used to doing that, that's okay. I will just put each separate case in a distinct column rather than just putting it all underneath one copy of the formula. So let's build it up in stages. Here are the 4 different cases, just as before, for what the combination of the input variables P and Q could be. False, 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 true, true, false, true, true. So then, what do we need? Well, we're trying to determine the overall value of this thing, so clearly we need to know what not Q would be in each case. So we just negate Q, carried across. That's what not Q is. All right, but then inside the brackets, we now need P and not Q. Well, again, by appealing to the and truth table we've already got, we can determine what those results should be. And finally, the entire proposition we're interested in is not P and not Q, and so we use the not table simply to negate the previous column, and these are the output values in all possible cases. And since we've covered all possible cases, we've said exactly what this formula means for all values of P and Q, so we've given it a full mathematical meaning. So a key idea is that of logical equivalence. Let me give you again an analogy from your school day experience. Quite early on, you might write things when you're doing algebra like x plus x. But we could also write that 2 times x. They are equivalent. They always give you the same value, whatever x is. Or another example you will have all remembered be factorization. So a times brackets b plus c is equivalent to a times b plus a times c. Okay? So you're used to this idea. There are different looking formulae, squiggles, propositions, but actually when we dig into it mathematically, they are equivalent. That is to say, in all cases, they give the same output. So if we drew up a truth table for each of them and we considered the inputs in exactly the same order, the final columns in their tables, even though the 2 propositional formulae perhaps look very different, turns out, you know what? They're equivalent. They're really just saying the same thing. So that's a key idea to remember. Here's a very simple example which actually is similar to the factorization example I gave you from arithmetic a moment ago. So let's bring this to life just a little bit. I'm using P, Q, and R. They're convenient variable names. Well, let's suppose that P was, I'm solving maths problems. Q is it's Wednesday, and R is it's Thursday. So the intuitive reading of this formula then says, I'm solving maths problems, and it's Wednesday or it's Thursday. Here's a different looking formula. Clearly it's different. It's got a different bunch of squiggles in it, right? This one says, I'm solving maths problems and it's Tuesday, or I'm solving maths problems and it's Thursday. They are logically equivalent, as you can check out. Look at all 8 cases. You are either are or are not solving maths problems. It either is or is not Wednesday, and it is or it is not Thursday. And in all 8 cases, the true or false value of this is exactly the same as the true or false value of this. So then, there are formulae that say the same thing, although they look different. They are logically equivalent. Pushing that to an extreme, we have certain formulae which are always actually just saying true. And there are others that actually always just say false. So a proposition that's always true, it's equivalent to just true. You always get true. Never mind what the value of the inputs is, the result is true. We call that a tautology. And the very opposite of that, a contradiction, is no matter what input values you consider for the variables, the value that you get as a whole is just false every time. We call that a contradiction. So here are very simple examples of both of those. P or not P. It sounds like a quote from Hamlet, almost. Okay, but think about it. P is either true or false. Or, as our colleague over here told us, the intuition behind or is you want to sense. Is there any true signal on any input out there? Well, look, one of these clearly must be. Because if P is true, well, then P is true, so that's it. But if P is false, then not P is true. So either way, one of these inputs, sure, will be true. So it's always just going to give true as a result. On the other hand, the AND requires both inputs to be true. Well, we're clearly on a loser there, because if P may be true, great, but in that case, not P is false. And making P false doesn't help us anymore, because now P is false. So this is a tautology, this is a contradiction, there it is as a table. It's simply summarizing what I've just said. Okay, so now here's another little question for you. Both tautologies and contradictions are sometimes dismissed as useless. So if you get one of these political interviews on TV or something, you know, you get one of these smart sort of interviewers who's all very cool and sophisticated, and they're giving the politician of the day a hard time, and they drive them into a corner. Yes, but will the government do this? And then what will happen? And what will happen when Brexit takes place? And all the rest, and it's all going on. And finally, the politician says something, and the BBC interviewer jumps and says, "Ha! But that's a contradiction," as if it's awful. You know, the guy should more or less go out and shoot himself. But apparently, it's equally bad if it's tautologist. They say, "Oh, that's just tautologist nonsense." So what's slightly strange is that given that tautologies and contradictions are clearly in some sense opposites of each other, you would have thought that if one was terrible, the other one would be great. But no, apparently they're both really bad. Okay, I'm dressing it up a bit. But what's going on? In what sense are both tautologies and contradictions not always that much use to us? Okay, so discuss. We'll come back to you in just a moment. Okay, the clock is racing on, so must we. Any offers? Just very briefly. Now let me see. Yes, there's somebody over this side. Hello, come on in. Again. Okay, right. So one answer is, well, what on earth's the point of writing this great long formula when you might as well just put true or false? It's a constant. Okay, so there's a practical man speaking, you know, simplify it away. Why on earth would you say all this? Just if you mean constant true or false, just say so. Okay, fine, thank you. Any other offers? Yep.
Is it because if all the results are the same as the output for all of the inputs, then you're not really learning anything?
Yes, that is indeed, again, validity in both answers. But this is the particular point. If you work, the whole point about these logical formulas, we're trying to capture something. We're trying to say something accurate and exact and possibly quite deep about the nature of the world as we observe it, or the nature of the computer system we're designing. So we're saying, you know, our computer system is not just going to be any old computer system, it's going to have this property. This will be true. And if it turns out that, well, any design that you came up with would have that property, it's you know, no matter what you did, you'd have that. So frankly, you haven't told us anything about your design by saying, oh, but this will be true. Well, it always would be. Plug in true or false all over the place. So it doesn't tell us anything. Okay, but what about a contradiction then? So that's tautology's been pinned down what it is that we, okay, so not always so useful. Tautologies have their uses. We'll come back to that. What about a contradiction? Yes. Okay, thank you. So you've neatly flipped and you've anticipated what's on the rest of my slide here. Indeed, if a tautology is true in every possible world, a contradiction is true in no possible world. So, you know, interviewer again, you know, now then, says the politician, I promise you this, when our party forms the next government, we shall not raise taxes, and we shall raise taxes. Well, you know, hang on a minute. You can't do that. There is no world where you do raise taxes and you don't raise taxes. Sorry, you're not helping me here. You're describing an impossible world, which may be interesting to some, but it's sheer fiction. And for example, if we're trying to design a computer, designing an impossible computer is not usually very useful. Okay. We're going to race through these next couple of slides fairly quickly. Do not be alarmed. You're going to get a chance to practice working with these laws. So here's what I'm calling Theorem 1. I've mentioned the word algebra. I've pointed out the analogy with things you know about arithmetic laws. So here are some of the laws that we have algebraically. So they have funny names, don't worry about those. Idem is Latin for the same. So if you've got the same input, then whether it's an or an and we're looking at, the output is again just that same thing. Excluded middle, we saw this a moment ago as an example. So P or not P, one of those must be true. There isn't a middle ground. And similarly, P and not P, they can't, one of those is going to be false. There isn't a middle ground where somehow both P and not P are not quite true or not quite false. That's called excluded middle. Identity laws, if you have a false as an input of an OR, then the result will be just the other input. If you have a true as an input of an AND, the result will be just the other input. Strictness, this is the case where a true or a false forces the output. The other input then becomes irrelevant. So this T here forces this one, this F forces this. And then finally, double negation, not P, is of course just back to P again. And notice how they all come in pairs. And that's because of this nice mirror property, that and or are mirrors of each other. So we've only got, this works because all we've got is and or not. If we have true and false, true becomes false, false becomes true. So in that world, we get this nice flip around property of that it can mirror all the laws. Well, at this stage, all we've got in our toolkit of truth tables So if you didn't believe one of these laws, one way you could check it is say, come on then, construct the truth tables and observe that the results are indeed the same in all cases, which is our basic meaning for an equivalence. We can carry on. There are some more laws. These ones involve two variables now. Associativity, we can chain either ors or ands, not a mixture. We're not talking about mixtures, but just a chain of ors or a chain of ands. It doesn't matter where we put the brackets. That's associativity is the technical name. Commutativity, which input is which doesn't matter too much in an and or an or. So P or Q is the same as Q or P. Same with an and. Here's distributivity. We had this as an example a moment ago. Problem solving on Wednesdays and Thursdays. So here's the, we're problem solving either and or, Wednesday, Thursday. But notice here the mirror property is true as well. We looked at the second of the two as an illustration a moment ago, but its mirror is equally true on top. And then finally, you can think of this as being the mirror law. More properly, we should attribute it to the mathematician De Morgan, who did some of the early investigations of propositional logic. So what this is saying then is that an or whose output is negated is equivalent to an and whose inputs were negated. Okay, so that's the De Morgan rule and its mirror, swapping and for or. So, in case you wonder, I've been using brackets here and there. There is a priority order. Quick sample. We shall finish in a moment, but let me just take this quick sample. If I say BODMAS, to how many people does that mean anything at all? Okay, that's fine. And to how many people does this mean nothing? You think I've lost my senses, which could happen sometime, I suppose, but right, okay, that's interesting. It varies from year to year. BODMAS, brackets of division, multiplication, addition, subtraction. So if there aren't any brackets, how do you know in what order to do a combination of divisions, multiplications, additions, and so on? So in the logical world, high priority, the things we attend to first, right at the top, there's not, then and, or implies if and only if. So you can use that fact if you like, but it is never wrong to put the brackets in. So there's an illustration of the point I've just made, but it's never wrong to put the brackets in. If in doubt, be safe, put the brackets in. So wrapping things up, I will always try to do that just at or just before 25 past. I shall always try to begin at 25 to. So key point summary then, as we finish this first of 12 lectures. This is, note, just a summary of some of the key points. It's not everything you need to know, but it's some of the key points. We've seen propositions. We've introduced those. They're squiggles. They're mathematical formulae. But they are truth-valued formulae, and we can say what their meaning is completely by drawing up a truth table. We saw this key idea of logical equivalence. Different-looking propositions may actually mean the same thing. We defined exactly what that meant. They've got the identical final column if you constructed their truth table. And lastly, we saw some example algebraic laws of equivalence, and we noticed that a lot of them come in mirrored pairs, which we like. Thank you for your attention. I'll see you later in the day. Hi.
Something that's confused me for quite a while.
Yes.
What's the difference between if and only?
We are going to be discussing that in this afternoon's lecture.
Okay.
So you ask me again if you're still confused after this afternoon's lecture.
Okay, thank you.
Hello.
I had a similar situation. There's a few things I'm still a little bit confused about.
Yes, fine. So I'm very happy to try to answer brief questions in this little slot just after a lecture. One of the purposes of the problem-solving classes, we don't just say to you, here are your problems, solve them. we come round, myself, a couple of graduate students, and I'm asking, everybody okay with lectures, anything you didn't understand? So we're going to have 2 hours to do that in your problem solving class. So if you're in a lecture, try to make a note as you go along. Oh, I need to think some more about this. That's fine, all right. Do not panic, it's fine, it's okay. I know it's this new, compared with perhaps the classes you're used to from school or college. Right, each lecture is just right, this, that's that topic, bam, next one. Okay, so that may feel a little bit, whoa, okay, that's it, it's gone. Yeah, it has, but it doesn't mean that's your last opportunity to think about it. We have 2 hours in problem classes, and the problem classes are connected very directly to the lectures. So here's some exercises and problems to help you get your head around lecture 1 and 2, right? So I would say, wait and see how you feel during the problem